After understanding what derangements are, now let's talk about number of permutations with fixed point. Take note that if we don't have any fixed point, we call it a derangement. So for example, as illustrated in the previous video, we have 1, 2, and 3. There are only two derangements. We have 2, 3, 1, and 3, 1, 2. There are only two derangements, meaning they are permutations where the positions or placements of specific numbers or elements are not on the same placement. Okay? Because if we're going to have here, say for example, 3, 2, 1, we have seen that there is actually a fixed point here. And that's the purpose for this next video. After understanding the arrangements, let's talk about the number of permutations with the fixed point. It anchors the idea of derangement because we're going to look at the possibility of having a number which is in the fixed point and the other should be in its derangement. Meaning, say for example, this is a fixed point. We know that 3 and 1 are also, if you're talking about 3 and 1 alone, they're actually examples of derangement. Now, there is a theorem or the formula in identifying the number of arrangement or permutations considering a fixed point. Say for example, this is how it is stated: for integers n, r, and k such that our n is greater than or equal to r, which is greater than or equal to k, or greater than or equal to 0, or if you would like to, you could also rearrange 0, k, r, n, meaning n is the number of objects. So you have here the number of objects in a set. R will be the number of the objects that will be arranged in terms of the arrangement, and k, this is the r, and k would be the number of fixed point. In this situation, our n here is the number of objects. In this case, for this example, we have here 3. Our k will be the number of fixed point 2, and of course, we're going to arrange all 3 of them. And that's what it meant by talking about this theorem. But this is not yet done, so pardon for that. And then we have here, and r is strictly greater than or equal to 0. Okay, so we have to arrange r objects from n objects at a time. So you will have here this formula: d n of r and k. This is still under derangement, but since it is anchored on the idea that there is a fixed point, we have this formula here: r combination k over n minus r factorial times the summation of -1 raised to I, r minus k combination I. We have here n minus k minus I factorial, where I starts from 0 until r minus k. Okay, so this is the formula or the theorem which stands for the number of permutations considering the idea of derangement, but considering that there is a fixed point in this manner. Okay, so let's illustrate it using this example. As we know, there are only two derangements, but for a fixed point, how many permutations are there considering that there is one fixed point? So let's say, for example, again, the set containing 1, 2, and 3, and we would like to know the number of permutations if there is one fixed point alone. So with that, our n is 3, our k is 1, our r, since we'll be using all of them, okay, so 3 as well. Using the formula, you have here d of 3, 3, 1. So you have here r taken 1 over 3 minus 3 factorial summation of -1 I, where you have here r, which is 3 minus 1 taken I. You have n is 3 minus 1 minus I factorial, as we have here I starts from 0 and 3 minus 1 for r minus k. This is a multiplier, so let's separate that. 3 combination 1 is obviously equal to 3 over, you have here 0 factorial in the denominator, times, let's simplify the rest first before expanding that. So summation of -1 raised to I. So you have here 2, sorry, this is I, combination I, you have here 2 minus I factorial, where I starts from 0 to 2. So again, this is 3 over 1. That's obviously 3 over 1 because 0 is 1 factorial times the expansion. You have negative 1 raised to 0, 2 combination 0. We have here 2 minus 0 factorial plus negative 1 power of 1, 2 combination 1, 2 minus 1 factorial. And you have here plus negative 1 squared. We will end up until 2 alone. So you have here 2 combination 2, 2 minus 2, you have raised to the power of 2. It's not, it's minus I factorial. Okay. So this is equal to 3 times 0, negative 1 power of 0 is 1, 2 combination 0 is 1, so you have here 2 factorial. Okay, so plus, you have negative 1, power of 1 is negative 1, 2 combination 1 is 2, 2 minus 1 is 1 factorial, plus, negative 1 squared is positive 1, 2 combination 2 is 1, this is 0 factorial here. So you have 3 times, 2 factorial is actually 2, then minus 2 here as well, plus 1 taken out at 0 is 1 factorial. So you have 3 times 1, you will get 3 permutations with 1 fixed point. Okay, that is for this set here, considering 1 fixed point. Let's try to manually list them if we can. So for our set 1, 2, and 3, in this specific pattern, there are only 3 of them. Let's try to check if this is fixed point, 1, 3, and 2. That's 1 already. Next, if this is the fixed point, so you have 3 and 1, that's another one. And if this is the fixed point, 3, you have 2 and 1. There are 3 of them, obviously, because the other will actually have different fixed points. So for example, if you have 1, 2, and 3, 1, 2, and 3, that's actually 3 fixed points. So that's different from that. And of course, we have also established that there are also 2 derangements to this. There are no fixed point. We have the items 3, 1, 2, and 2, 3, 1. These are derangements for this. So 0 fixed point, 1 fixed point, and the 3 fixed point of 1, 2, and 3. So this shows the number of permutations for this situation using the formula. Now in the next video, we will have a different n and k, or even r for that, to establish the number of permutations with fixed points, considering the number of arrangements, that some of them are derangement. And at the same time, the reason why this is included in the playlist for principle of inclusion and exclusion. Thank you very much for watching.